everyone, and welcome. I am Avi Kivity, CTO of CyllaDB. And in this presentation, I will talk not about any particular feature, but about how scalability is a feature in itself and how it interacts with all other features. So let's start. Enough about me. So first we'll discuss scalability in general, and then we'll look at a few case studies from ScyllaDB itself. So what is scalability? Everyone knows that. It's the property of a program that as you add more resources, it goes faster. And it's expected to scale linearly. So you double the number of nodes, you expect double the throughput. And it doesn't mean that an individual node is fast. It just means that as you increase the number of nodes, then you get better performance. But that's a good textbook definition, but it's less practical. A practical definition of scalability is that as you increase the amount of resources, you get an increase in throughput. It doesn't have to be exactly linear because you may have to sacrifice a lot to reach linearity. So it's enough to be near linear, and you don't have to scale indefinitely. It's enough to reach some reasonable limit that is sufficient for the workloads you target. And you cannot sacrifice the single node performance because people do start with small systems and then they grow. If you start with low single node performance or low small cluster performance, then it becomes impractical, and as you scale, it also becomes very expensive. So we need to keep single node performance high. So horizontal and vertical scalability, who did that? So horizontal is what we just discussed. You scale with the number of nodes, but vertical, it means scaling with the size or the compute power of individual nodes. And in the last decade or so, it became very important because nodes started growing huge numbers of vCPUs, and it's quite a chore to be able to utilize all of them. And they are both important, and we'll see why. So why horizontal? That's relatively simple. Any node size, no matter how large, will be limited in the end. You also want it for geographical distribution to get low latency to your customers, and you want high availability in case a node fails, fault tolerance. So you do need horizontal scalability, but it's good to look at the size of today's nodes. So below is the largest storage node from Amazon. You can see it has 192 vCPUs and 1.5 terabytes of memory. And if you multiply the number of devices, 16, by the size of each individual device, you reach a whopping 120 terabytes. So that's quite a huge node. And if you look at the image on the right, this is a similar processor from AMD, which also has 192 vCPUs. And you can see that even though we're talking about vertical scalability, the CPU itself implements a sort of horizontal scalability by aggregating cores into CCDs and aggregating CCDs into the processor. So, and we agreed that horizontal scalability is great and necessary, but why vertical? So when you have small nodes, the overhead quickly dominates. You need to leave some memory and some CPU for the operating system. You get networking overhead. And if you reach a cluster that has a size of 1,000 nodes, and let's say you have a 3-year mean time between failure, it means that every day you will wake up to a failure if you're the one that has a pager number on that cluster. Things like upgrade become hell. You want to upgrade the cluster, you need to upgrade 1,000 nodes. It's 1,000 chances for something to go wrong. And I asked some AI about what is the largest Cassandra cluster, and it spat out that it's a cluster that operated by Apple that has over 1,000 nodes and multiple petabytes of storage. And this isn't intended as a dig at Apple, but this is just crazy, because if you look at the nodes that we had in the previous slide with 120 terabytes, then 20 nodes would supply you with multiple petabytes of storage. You don't need 1,000 nodes for that. So Apple, if any of you are watching this, our operators are standing by to take your call. So why both? So first, when the work for horizontal scaling also benefits vertical scaling. You saw the image of how the large processor with 192 vCPUs is basically a small cluster, or maybe a large cluster. And here is the image of the infamous image of the puppies. And if you use a thread per core architecture, then you basically get all of the benefits of horizontal scaling apply also to vertical scaling. And when you have a reasonable cluster size, then you get lower maintenance and lower failure rates. And you benefit from geographical distribution, so you do need this horizontal scalability. And if you imagine a large cluster, 100 nodes, with 120 terabytes per node, that translates to 12 petabytes. So that's a huge cluster, and I imagine very few of the audience need to operate such huge clusters. So scaling up to 100 is enough if you have access to large nodes, which are practically industry standards these days. They're not exotic in any way. So it should be enough for anybody. So what are our goals? So first, we need fast algorithms and implementation. Goes without saying, if you want fast single node performance, you need fast algorithms and to implement them well. And you need good scalability in order to actually scale to these sizes. And you need to make practical trade-offs. So don't sacrifice one important feature for another. So fun fact, the name Scylla was chosen to remind people of scale, but then we learned how it's pronounced, so that didn't work as planned. So what are our practical scalability goals? So first, 100 nodes per data center, and there can be multiple data centers in the cluster. So a few hundred nodes per cluster should be enough. And in terms of the size of individual nodes, so we're targeting 256 vCPUs that have around a terabyte of RAM. And we can follow the industry as it grows. The vCPU count is growing, but it's not growing very rapidly. It's growing maybe 50% every couple of years, and that's slow enough for us to catch up too slowly. So what are the components of performance? So again, good algorithms and data structures, scalability, both horizontal and vertical, and an efficient implementation. So C-Star. C-Star is our I/O framework, and it builds on the fact that if you're building a cluster application, then you already solved the problem of sharding and distribution across nodes, and you can just reapply the same solution on individual compute cores. So it breaks down the node into a sort of mini cluster that is composed of individual vCPUs. And while I talked about how efficiency is important, C-Star does sacrifice some efficiency in order to get high utilization. So we're not going all out for efficiency. It's okay to sacrifice some of it, but in return, you get that all of your vCPUs are working, and they're not just watching one vCPU working hard. Instead, all of them work towards the goal. And this sacrifice involves breaking down each compute task that has to be performed into smaller parts. And of course, this increases overhead, but it allows the individual cores to run multiple tasks in parallel and therefore not require multi-core communication. And here's an example. You've seen it already on Dora's presentation, but it's a good one, so it's worth looking at again. How you can have a node with around 100 vCPUs, all of them going full tilt. So this is your machine working for you and not just idling by. If you bought the machine, you deserve having it work for you. Okay, so next, let's look at another case. Let's look at how we size memtable and cache. So for those who are not familiar, CyllaDB uses a log-structured merge tree. And the first step of the log-structured merge tree is to fill memory with data, sort it in memory, and then spill it to disk. And the question is, how much memory do we allocate to memtables? How much memory do we allocate to cache? How much memory do we leave free? So let's look at the log-structured merge trees. And if we compute, I'll have to say that this is an oversimplification. Reality is a little bit more complicated, but the conclusions still hold. So right amplification in a log-structured merge tree is O log n. There's no big surprise here because all of those algorithms, they always turn up to be O log n. But what is n in this case? And it turns out to be the size of the largest SS table in the merge tree divided by the size of the smallest SS table in the merge tree. And the size of the largest SS table, again, oversimplifying, is the disk size. And the size of the smallest SS table is the memtable size, which we sorted in memory. And since we want large nodes, we want a large disk size. So that grows our n. And since we want to reduce the fraction, we need to have a large memtable size. So we must choose the largest memtable size that we possibly can. So what we do is we allocate half of the machine's memory to memtables, and the other half for cache and incidentals, which is what we call request memory and memory needed to hold connections. So we divide it equally, half and half. How much do we leave free? So ideally it would be nothing at all. So memory should be working for you and not being idle, being free. In practice, we leave about 60 megabytes per shard or per vCPU, so that allocations can be served quickly without eviction. So why half and half? How did you come up with those numbers? So we did a rough sensitivity analysis. And if you look at the 50% allocation, then if you make a 5% change, so it changes to 55 and 45, the change has the same impact on the memtable and the cache. But if you're at 90-10, then let's say you're adding 5% to the memtable, you reach 95% and 5%, it has a small impact on memtable. It just changed from 90 to 95, but a drastic impact on cache. It halves its size from 10 to 5. So the place where it evens out is 50-50. That doesn't mean that it's the optimal division for every use case, but it's the one that is least sensitive and will cause the least surprises. So we pick 50-50. Next, let's look at global indexes. So there are multiple solutions to choose from. There's I'm comparing here to Cassandra, but we could compare to other databases as well. It's just an example. So let's compare to Cassandra secondary indexes, the CyllaDB global index, and the near Cassandra storage attached index. So let's look at Cassandra secondary index. It's a fairly old technology from the early days of Cassandra. And here, each node is responsible for indexing its own data. So you have your main table, and you also have an index table, which is local to the node. It's not a distributed table. And if you add a node, then you have to rebuild the index on that new node, and you have to clean the index on the other nodes in the system. So there's some maintenance involved. And the bigger problem is that the amount of work scales with the number of nodes. It depends on the index type, but for global indexes, it scales with the number of nodes. So if you double the number of nodes, you also double the amount of work. And so it's sort of anti-scaling. When you double the number of nodes, you expect to get more throughput, but here your throughput remains the same. You do have more resources, but they have to do more work. Let's look at the ScyllaDB global index. So it uses a materialized view to store the index. So instead of having a local table per node for the index, we have a global table that is distributed that stores the index. It's distributed in the same way that the data is distributed, but because the keys are different, there is no one-to-one relationship. So you don't need to do any additional work during the bootstrap, but you do need additional hops to access the data. So when with a local index, the data is always on the same node you're accessing. Here you have to do an extra network hop, which adds latency. However, and that's the important part for us, the work does not scale with the cluster size. So if you're adding more nodes, you will get more throughput out of your index. It's not perfect, however. If you have columns that have low cardinality, they can cause large partitions, and they can also be hot partitions, which are a problem. So it's not a perfect solution, but for workloads which are well prepared, it scales very well. And finally, let's look at the Cassandra storage attached indexes. So this is taking the idea of a local index and taking it to the extreme. Instead of each node having its own index, every SS table has its own index. So one benefit is that it supports complex queries, and you can do range searches and free text searches. So that's a nice benefit, not just simple matches. And the index is rebuilt during compaction, so the work is reused. It's more memory efficient. So I mentioned before that having efficiency is important. But the work, instead of scaling with the number of nodes, it now scales with the number of SS tables and in the cluster. And for us, that would be terrible, because with the move to tablets, we have a very large number of SS tables in the cluster. Each tablet contains its own set of SS tables. So large clusters would have a huge number of SS tables, and index searches would be excruciatingly slow. So let's compare the various indexes. So you can see that each solution has an anti-scaling with something, except for the global index. And this is indeed what we chose. If we implemented a local index with ScyllaDB, it would be even worse than with Cassandra, because instead of anti-scaling with nodes, it would be anti-scaling with shards or vCPUs. And of course, there are a lot more vCPUs than there are nodes in the cluster. So we chose the one that scales, even if it does come with some efficiency cost. Next, let's look at vector indexes. So with a vector index, you cannot extract a partition key. The vector itself is not really interesting because you're not searching for the vector itself, you're searching for vectors that are similar to the input vector. So you cannot use the global index example that we used for regular indexes. And the index computational complexity is, I hope no one is surprised, it's again O log n. All of those algorithms are O log n. And let's try partitioning the index in the same way that we partitioned dividing the index into nodes. So if you have P partitions, P could be your node count or your tablet count, then you multiply log n over P, which is the computational cost of searching any node's index, by P is the number of partitions, and it turns out that log 1 over P is negligible, so it ends up that you anti-scaled and the cost multiplied by the number of partitions. So if you have an index on every node, then the amount of work increases by the number of nodes. If you have an index per tablet, then it increases by the number of tablets that you have on your cluster. And of course, we do want to have lots of tablets, so that wouldn't work for us. So what's the solution? We chose, because we saw that partitioning across many nodes will not work, to use vertical scaling and have a small number of very large nodes. So take the very largest nodes that we can, or at least the ones that are needed for a particular problem. And instead of adding nodes, prefer increasing the node size. Of course, that cannot go indefinitely. So eventually we start duplicating data. Instead of partitioning the data, we start duplicating it, and that increases the throughput. If the node size limit is reached in terms of memory capacity, then you start partitioning it as well. So the downside of this is that you have an asymmetric architecture, which means that scaling the data cluster and scaling the index cluster is done separately. So it increases the complexity, but increasing the complexity is a reasonable price to pay for this difficult problem in order to have a scalable solution. And as a bonus, because you're using different node types, you can specialize a node type for the problem, and you can have a node with a GPU or a TPU or whatever in order to make the index run more quickly. So I love symmetric architectures, but in certain cases, it's better to use asymmetric architectures. So I updated the table for vector search. And if you have an asymmetric index type, then the anti-scaling is with the number of indexing nodes you have, but you're trying to keep them small, and the nodes large, but the number small, and you have increased coordination and orchestration overhead, but that's a price that you have to pay. Next, let's look at change data capture streams. So what is change data capture? Every time you write to the database, it generates a record in an auxiliary table that records the change. And in a way, it's similar to an index. An index gives you a copy of the data, but with a different key. And here, for change data capture, our key is time. And the question is, how many streams to use? And the obvious answer that the user would want is, give me just one stream and I will just pull the records one by one. And every stream that you add to the user, that's more effort. You need to store the position within the stream. You need to store it somewhere, and you need processes to consume those streams. So it would be best to minimize the number of streams. However, if you do that, you enter a scalability problem. So if you have one stream, the node that serves that stream becomes a hotspot, and you also have to synchronize all the writes to that stream. If you have one stream per node, then you improved something, but it's still pretty bad because you would have a shard within a node becomes a hotspot. So one vCPU would have to serve all of those streams. And our solution wasn't very complicated. It's just to have one stream per shard. So that's the minimum number that would actually scale. There is some complexity involved. The number of shards in the cluster can change when you add or remove nodes. So you need to keep track of that and close old streams and start new streams. And then you need to have a sort of meta stream that updates the user that streams were closed and be open. And this meta stream is just a single stream. And you can see that with change data capture, most of the complexity in the feature came from scalability considerations and not from the feature itself. So to conclude, scalability is in everything we do. We eat it for breakfast and lunch and dinner. And sometimes we sacrifice efficiency so that the cluster will not break down at scale. But we cannot sacrifice too much efficiency because we need to work well at low scale. And indeed, we can do 1 million operations per second on 3-node clusters. So we have to work at all of these sometimes conflicting goals simultaneously. And that's all from me. Hope you enjoyed.